Hello and welcome to video 2.5, where we're actually going to do some calculating with binomial and geometric probabilities. So we talked last time about the different settings, what's the difference, sort of what keywords to be looking for, and then got a little bit into sort of like, well, how would you calculate these things? And so some of them by hand aren't too bad. Some of them we're going to probably want to take a look at what our calculators can do. So we're going to start actually talking about binomial settings to begin. So binomial settings, if you remember, are always about like you have, some set number of trials and you're interested in how many successes in those trials. So I want to sort of go through a couple of examples here first about like, let's go back to that Pokemon card sort of example from last time. 20% of all packs contain a holographic card. So let's say we buy 5 packs and we want to know what's the chance of getting 1 pack in that hole that have a holographic card. So let's go ahead and get into that and think about, well, how many different ways is that possible? Take a moment to think about it. So what you should have said is 5 different ways that can happen. So, like maybe the first pack has it and nothing else, or the second pack, or the third pack, and so on and so forth, all the way to it's not until the 5th pack that you get a holographic card. So 5 different ways that is possible. Not too bad to think about and work through. But let's just ramp it up a little bit here. What if I bought 20 packs and I'm interested in how many different ways can I get 4 packs that have holographic cards? Think about that for a little bit. So hopefully for that one, you immediately made a frowny face, or maybe after some thinking made a frowny face, because it's a lot to try to think about how many different ways can you get 4 from 20, because it could be the first 4 packs. Or what if it's just the first 3, and then it's the 5th pack, the first 3 in the 6th pack, the first 3. You could see how this is going to be a lot of different combinations for us to work through, and it's probably not going to take just a minute to think about it. It's probably going to take a little while here. The good news is that somebody long ago figured out how to come up with this sort of combination number relatively quickly. And if you're ever interested in sort of digging into why the formula I'm about to introduce here makes sense, feel free to go and check out some of the resources in our master document there. But here it is. So if we're looking for any number of combinations that are possible to have k successes in trials, then that can be found with this formula right here. And maybe there's a ton of things that are kind of new to you there. So that weird little parentheses in k thing that you're seeing there, we say that as n choose k. So how many different ways can I choose k number of things from n total things? You also notice that there are some exclamation points in there. That is not because we're excited about these numbers. I mean, I am, but it actually represents this idea called the factorial. So we would say those things as like n factorial over k factorial times n minus k quantity factorial there. And so what does this n factorial represent? Well, generally, it is this idea that you take the number n, you multiply it then by every natural number underneath it until you get down to 1. Like so. So for example, 4 factorial is 4 times 3 times 2 times 1, which is 24 when you calculate it all out. And that one wasn't too bad. You can see how quickly this kind of explodes as a number, like even just doing like 7 factorial is not something you want to do by hand, really. It's a little bit messier. So this is where our calculator can help us out, and this formula actually can help us out too. So for example, in this previous example, we were thinking about like, all right, well, what if I bought 20 sort of packs and 4 of them had the holographic cards in them? So 20 choose 4. Well, let's calculate that out by hand, but then we'll let the calculator actually help us out with these things. But I just wanted to go through one example with you. So 20 choose 4. So according to the formula, that's going to be 20 factorial over 4 factorial times, and then that's going to be n minus k. That's going to be 16 factorial. Cool, and so like I said, we could go grab a calculator. There is a way to find factorial on your calculator, but actually these formulas work really well because since you're adding like the same, you're multiplying these factors together, they tend to duplicate themselves. So like, just want to show you, like this, up here is 20 times 19 times 18 times 17 times 16, ... all the way down to 2, 1. And then down below, we got 4 times 3 times 2 times 1, which we already figured out up here, so that's cool. And then this is 16 times 15 times 14, ... until we get down to 2 and 1. So what I would notice here is that this right here, 16 times all the things below it, that is the exact same factor as this one here. So it turns out those divide away to 1, and all we're left with is actually 20 times 19 times 18 times 17, all over 4 times 3 times 2 times 1. So it's not as messy, not as many things you'd have to plug into your calculator if you were to do this sort of quote unquote by hand, but still let the calculator sort of multiply some stuff out for you. What it ends up being is 116 to 80 over 24, which is 4,845. All right, so there are 4,845 different ways that you can choose 4 from 20 things. That's a lot, and if we were trying to do that by hand, you could have seen that that would have taken us a very long time, lists upon lists. So it's not worth it. So yeah, that's sort of the idea here. So your big takeaway from this is more about like this notation here. When you see this, you should know that that means 20, choose 4, or in other words, how many different ways can I select 4 things from 20? And that is really the big takeaway from all this. The calculation, you're going to see that the calculator can actually do it for us. So let's continue on here. So since we can think about this probability again, about 20 choose 4, how many ways to get 4 from 16? Well, let's think about that for a moment. What is just the probability of getting one of those things? Well, it would mean that in my pack of 20, 4 of them were a success. So I got 4 successes there. And the rest, 16 of them, were failures. They were not containing the holographic card. So this is just one way. This is the probability of just getting it one way. But as we found out, the probability of getting this is not just one occurrence. There are over 4,000 occurrences of this. So let's write out our sort of final answer here. So the probability that we get 4 packs containing a holographic card exactly. So that's going to be 20 choose 4 times the probability of 4 successes times the probability of 16 failures. Notice that adds up to 20 total events there. And that is equal to, I calculated it already out on my calculator, just for the sake of it, to making things easy, because this right here is 4,845, and then I just threw that into my calculator, multiplied it by 0.2 to the 4th times 0.8 to the 16th, and got this number. All right, here's the thing though. Your calculator can do this for you relatively quickly. Let's take a look at that. All right, so let's go ahead and come up with our first binomial probability using our calculator. So what we were dealing with was that we had 10 Pokemon cards or Pokemon packs, and we were trying to see what's the probability of getting exactly 2. So to get to where we want to go, we're going to go back into our distribution menu. That's where we were finding our normal CDF, if you recall from notes, was it 2.2, I believe? So to get there, we're going to hit second, and then this vars button that's right here. And we're going to actually go all the way to the bottom. You can actually also arrow up and it'll take you to the bottom. And here we go. Here we are, binom PDF CDF. We're talking about exactly equal to 2. So that's a PDF, that's a point. So just x equals 2, that's a point, not c, which would be cumulative, like we usually do with the normal curve. We're interested in a cumulative probability. So here we're interested in just the exact probability of exactly 2. So here we go, press that. And so I'm gonna type in for my trials, that is gonna be the 10. And my probability was a 20%, so 0.2. And lastly, our x value, we're interested in exactly 2 packs, so that'll be 2. And then I'll come down and hit paste. If the menu didn't pop up for you, then that means you were probably have a slightly older software. And so this notation right here is exactly what you want. You want to go, that's binomial PDF, you're gonna go number of trials, comma, probability, comma, and then the number of successes. So I'm gonna hit enter, and there it is, 0.3019, I'll round that up, 0.3020 is what I'll call that. So there's binomial PDF for us. All right, so that's how you can calculate a binomial PDF, P meaning point again, that we could do here very quickly. So that's the idea. So I wrote down here sort of the TI command. If you're somebody that owns an older TI calculator, then you didn't get the fancy menu that popped up for me, but you can sort of type in this syntax right here. So we're talking about number of trials, comma, the probability, comma, number of successes. So now that we got that notation out of the way, we can sort of boil down probability to some real hard and fast rules here. So here is a box that sort of explains all the things. First, we define some variables. The one that we haven't really mentioned yet is Q. Q is just sort of our stand-in for probability of failure. So it'll be 1 minus P, since we're dealing with binary sort of Bernoulli trials here. And then expected value and standard deviation are right there, okay? Again, if you really want a proof of why those things work, feel free to look at our resources in our master doc, but we're just gonna go with that you know them and can use them. And then here are some sort of ideas about how we represent binomial probabilities. So we have that notation from last time here, and where X is the number of successes in trials, here's the calculation for it all, which we just sort of saw above. We have here that we're going, 20 choose 4 times the probability of those number of successes times the probability of those number of failures. And so if you're wondering like, well, that's a lot of things. Do I have to memorize all of this? And you probably are familiar with at this point that no, usually we don't have to memorize all of this. As we can see right here, this row contains basically all of that information. And it doesn't quite explain the N and P, so that's really the only part you'd really need to like quote unquote memorize. But we can see that it tells us all the things here. We've got our expected value, mean, right there. We've got our standard deviation. Instead of Q, they use the very explicit 1 minus P, which is actually kind of nice. And then we can see here, they tell us how to find the probability of the first, or of X successes in a number of trials over here. Again, they don't really explicitly say what is X, what is N, what is P. That's something for you to know, but it's all right there for you. So let's go ahead and actually take a look at some problems here, practicing our skills. So first one here. If you purchased 10 Pokemon packs, what's the expected number of packs with a holographic card that you would get? Why don't you think about what you would use from this above box to calculate this? So hopefully you said that you would be using the expected value theorem there. And so it is the number of trials times the number or the probability of a success there. 10 times 0.2, which is just 2 packs. So hopefully actually right there, that that rule for expected value totally makes sense, because if I said, hey, there's a 20% chance of getting these things, you bought 10, how many do you expect there to be? You'd say 2, because 2 is 20% of 10. So that hopefully that formula for expected value totally makes sense. Maybe standard deviation doesn't, and that's okay. That's where maybe you'd want to go and check out the video if it really is bothering you. All right, let's take a look at part B. So what if we bought 10 packs and we were interested, what's the probability that exactly 2 of those packs had holographic cards? So like that's our expected number, right? But like how often does that actually happen? It's not 100% of the time. So how would we sort of do this? So look back at the previous example and write out an expression that would represent this. So the probability of getting 2 packs with holographic cards, so x equals 2, that would be 10, choose 2, times 2 successes, times 8 failures. So we can calculate that out in our calculator, so go ahead and do that to remind you of how to use the Binomial Cdf. And so you should have gotten 0.3020. All right, let's take a look at letter C. What if we bought 10 packs and I was interested in the probability that I get 2 or less packs with holographic cards? Okay, so this time around we're interested in what's the probability of getting where our x is less than or equal to 2. Okay. So this isn't too crazy to think about. This is asking essentially like, well, what if I got it in 2 exactly? That's the above probability right there in part B. But this question also has us thinking about, well, what if I got 1? Or what if I got none? What if I got really unlucky and it turns out I got none? Well, what I could do is I could use my Binomial Cdf from my calculator and calculate each of these things, 3 individually, and add them all up. That is totally feasible. But it turns out our calculator actually has a way for us to sort of do this. So let's jump over to the calculator. All right, let's go ahead and take a look now at using Binomial Cdf. So rather than calculate all these ones individually using the Cdf function and then trying to add them all up, our calculator allows us to come up with cumulative probabilities relatively quickly. So we're going to go to the same menu before, second, vars, which is actually our distribution menu. And we're going to go down to the bottom again, and letter B is Binomial Cdf. You'll notice that the menu that's in front of us looks exactly the same. So let's go ahead and type in. We got 10 trials. The probability is 20%. And we're interested in having it happen in 2 or less trials. So, 2 or less successes. So it's going to be 2 there. All right. And by plugging that in, it's including 2. So this isn't strictly less than 2. This is including 2. So this is going to be what if I get none, what if I get 1 pack, or what if I get 2 packs that include the holographic card. So I'll paste. You'll notice it looks identical to what we were typing in before, except for now it says CDF. And when I hit enter, there it is, 0.67779. I'll round that one up to 0.6778 for us. So that is Binomial Cdf. Alrighty, so what we found was that the probability is 0.6778. And so I have written down here sort of what we typed in the notation. So Binomial Cdf, C standing for cumulative, 10 trials, 20% probability, 2 successes. And I decided to draw a little miniature sort of distribution to get us sort of seeing like, if this was our binomial sort of distribution, maybe it's not as symmetric, maybe it's supposed to be a little more skewed, but what it found for us is the area under this binomial sort of distribution to the left of 2. Note that that matches with what sort of our normal curve, our z-score table does for us. It's always a left-hand sort of area, left-hand probability, always less than that. So it's consistent with that. So that's something to always keep in mind, is that CDF is from the left side, left-hand sort of probability. Let's do one last one, and by that I mean actually you're going to do it, but I'll sort of set you up here. So now, what if we bought 10 packs, and I'm interested in the probability that I get more than 2 packs with holographic cards? How do you think you might be able to find that? Hint, you can utilize some of the work we've already done. So think about what might actually help us out here and how to use it. And when we come into class, we'll talk about that one. All right, on the backside, we're jumping into geometric probabilities. This one we don't have a whole ton of like setup because we can actually jump right into it. No new notations or functions for us. So here it all is. First line there, we've got our notations for P and Q. And then what is our expected value? What is our standard deviation? And then sort of how we sort of find probabilities and note the model and things of that nature. So it's all right there. Let's go ahead and jump into some of these examples. So here we go. First one. So we're talking about 8% of men are colorblind as a sort of stat. A researcher needs some colorblind men for an experiment and is testing potential subjects. On average, how many men should the researcher expect to have to test in order to find one that is colorblind? So what do you think that's asking us to calculate? Think about it. So hopefully you were thinking, oh, that's expected value. It says expected right there. So yeah, that's 1 over P, 1 over our probability, which is 12.5. And if you're wondering, well, how do you have a half of a person? Remember, this is just an average, and so it is not saying that's, you know, every single time it takes 12.5 men to go through. And instead, this is thinking more about, like, on average, it's 12.5. Your center will be at about 12.5. You might get as low as the first time somebody is colorblind, and it might take you 25, 50 times until to get to them. But on average, 12.5 is what it is. Okay, let's take a look at the next one. What's the probability that the first colorblind man found will be the 5th man tested? We know this is geometric because it's talking about when's the first success. We don't have a set number of trials that we're interested in, how many successes within there. It's like, when is the first success? So this one, we're finding the probability that X is equal to 5. So first, let's just do this by hand and sort of make sense of sort of this formula up here. Which, by the way, I forgot to mention. Right here, this is our geometric probabilities. You probably noticed it the last time I was here. But you can see we have here the mean, the standard deviation. Again, they don't use Q in their sort of setup there. And it looks a little bit different than what we have here. But it really is the same, like algebraically, the square root of P squared is just P. So they've sort of done that for us already here. But either one's fine. And then again, there is this, like, how do you calculate the probability here? And so we're going to talk about, like, well, why does that sort of formula make sense? Well, let's think about this. Let's imagine we are the researcher. So we're pulling people randomly from this pile and sort of going, like, are you colorblind? And according to this, we get 4 no's in a row and then finally hit a success on the 5th time. So it's like, the first person we pull is, no, I'm not colorblind. Well, the chances of that is 0.92. Second one, also not colorblind. Third, fourth. These are all independent events, so I can just multiply them together like this. And then finally, the 5th one is our first time of seeing someone who is colorblind. A different way of writing that, that's maybe a bit shorter, would be to write 0.92 to the 4th times 0.08. And let's pause to note that that is sort of the form that we're seeing up here. You're going to multiply Q together, X minus 1 times. Okay, Q, remember, is probability of failure, 1 less amount of times than when we first see our success, and then times the success there at the end. And so that gets us, when we calculate it all out, 0.0573. That's a 5, an ugly 5, but we'll go with it. Well, as you probably guessed, your calculator can actually do this too relatively quickly. This was pretty quick, but you will start to see that there may be sometimes we'd want to use the calculator to make it way more efficient. So let's jump over there. All right, so we've gone through binomial, let's go geometric. So a geometric PDF, I bet you probably could have done this without the video, but I'm gonna show you anyways. Second, vars, taking us to our distribution menu, head all the way to the bottom, and at E is geomet PDF. So go ahead and hit enter. And nothing really unexpected here. What is our probability? In this case, it is 8%. And where are we thinking about our first success is going to be at? We're wondering about when is it the first success at the 5th person. So exactly equal to 5. Hit paste. For those with the older calculator, there's your notation right there. Probability, comma, X, or when the first success occurs. And we hit enter. 0.0573. So there's geometric PDF. Alrighty, so there you have it. And that's a great way to do it. Like I said, this one wasn't so bad by hand. You know, I feel comfortable doing it. But ultimately, if they were asking about, you know, much later trials, writing it out by hand is not the most fun. And calculating it out by hand is maybe not the most fun. All right, let's keep going here. What is the probability that the first colorblind man isn't found until, that the first colorblind man found will not be the 12th man tested, okay? Will not be. So we're interested in here, what is the probability that X is not 12? Well, how do you think we would find that? Think for a moment. So this would be sort of really difficult to try to find through what I'd call brute force, where we go well, what's the probability it's the first, or the second, or the third, or the fourth, or the fifth, or the sixth? Keep going. 11th. Oh, skip 12. 13 and 14 and 15 and 16. And then how far do I have to go out? Well, theoretically, I guess we could never find one. We could just keep polling forever and ever. It's possible, not likely, but it's possible. And yeah, that wouldn't be a good idea here. So this is actually one of those hidden complement problems where we would say, well, the probability should all add up to 1 in our probability space, and I just don't want that it's the 12th person. So I'll just find that probability that it is the 12th person and subtract it from 1. So go ahead and do that, either by hand or using your calculator, or ideally both. All right, you'll check that answer when you come into class. Let's move on to D. What's the probability that she finds a colorblind man within the first 4 men she tests? All right, so the probability that it happens within the first 4. So that includes 4 there. So this is thinking about the probability that maybe it's the first person, or the second person, or the third person, and lastly, the 4th person. All right, well, here we are. We're in an example here where we're just got to find 4 things like we did in part B up here. So I guess we could do that and write it all out. But again, that's a lot of writing out of things. I like writing this out to really give me a clear understanding, but I bet you probably saw in our calculator that we have a function that will help us figure this out much more quickly. Let's head there. All right, last one here, geometric CDF. So if we don't want to calculate, all of these individually, 1 and then 2 and then 3 and then 4 and add them all together using the PDF function, we can do this using the CDF function. So head back to that distribution menu, so second vars, go to the bottom, the very last option, option F there is geometric CDF. Click on that. Again, the menu looks very identical to the PDF one, but this time around it's going to be finding all the things less than it as well. So we're still at 8%. We're interested in the 4th or 3rd or 2nd or 1st person being the first person with color blindness. So this will include all of those. 1, 2, 3, and 4. It always includes the x value there. We will hit paste. There's that notation one again, and we'll go ahead and enter. There it is, 0.2836 as our probability. So geometric CDF. Okay, so what we figured out is that the probability is 0.2836. And I've written down here the TI notation for you. Again, if you have older formats, then you would type in the probability, comma, and then the X value, in this particular case, sort of the most amounts till we get a success. And then I drew a little distribution again. Remember, geometric is that like skewed right distribution. And so just noting that like the CDF function, oh, I didn't write CDF. Let's write that, CDF. That function is finding the left-hand probability here, not to the right of 4, but to the left, just like our z-score table, just like binomial CDF, left hand all the way. All right, so these last two I'll sort of set up for us, but I want you to work through them. So then what's the probability that she finds a colorblind man before the third man? So think about, how is that a slightly different question than part D, other than the fact we're saying 3 instead of 4. So here this time around, we're saying the probability that X has to be less than 3. So if you were thinking like, I still need to use that CDF function in my calculator, you're right. But remember, CDF functions include it, okay? So in our CDF function, this 4 is included. That was actually the same for binomial as well. Back over here, I could sort of note that this right here, that is included. We're including 2. So how do you think you would still leverage using that CDF function in your calculator in a way that helps you find this probability? That's for you to think about and come in for class to talk about. Let's move on to F. Last one. What's the probability that she does not find a colorblind man until at least the 15th man, sorry. So how do you think you'd find that one? Think about that for a little bit. If you need a little nudge, what you're really trying to find out here is what is the probability that our X is greater than or equal to 15. So you're going to find this, again, using the CDF function in a, cleverer way. So think about how to use that and why it makes sense. And then come on into class where we will talk about all the ones I left for you.